All right, so for the last two examples, one of them we're going to do is, I guess you could say it's a word problem. A little conventional, though. We're not going to be setting up equations to solve for specific values or anything, but let me kind of write this out for us. So, example number, I think I'm right on this, number 5. It says a manufacturer drills a hole through the center of a metal sphere. So drills a hole through the center of a metal sphere. And they say it's of radius 5 inches. They say the hole has a radius of 3 inches. So the hole has a radius. It's not how you spell radius. Of 3 inches. What is the volume of the resulting metal ring? So normally you could find the volume of the sphere, right? 4/3 pi r cubed, where r is 5. So you'd plug that in and you get your volume of your sphere. But then they say they cut a hole in there and they removed, created a hole that's 3 inches in radius, right? Now sometimes people say, well, in that case, then it's basically you're just getting rid of like this rectangular hole, but not really, because there is a little bit of a slant near the ends of that hole, right? There's going to be a little roundness to it. So it's not entirely just a block. So you can't just say a sphere minus a rectangle, and that's going to give you the resulting amount. Okay, so what we're looking at is something kind of like this. And drill a hole into it. And this is going to be the center of it, right, that they're rotating about. They said that the whole thing, right, so actually that's not correct, not the whole thing. The radius of this is 5 inches, and the radius of the hole is 3 inches. Okay, so again, manufacturer drills a hole through the center of a metal sphere of radius 5 inches. The hole has a radius of 3 inches. What is the volume of the resulting metal? Now, you got to think about this. This shape has already been getting spun around, right? They're already revolving it. So this is the shape you get when something has been getting turned over and over and over again really quickly. So now the question is, what does this shape look like in 2 dimensions that creates the shape that I see? Okay, so in a sense, what we're trying to figure out is, okay, I know I can get a circle that's flat, and if I put it against, let's say, this may not be perfectly lined up, but let's say I rotate it about the x-axis, right? If I spin a flat circle around over and over again, then I am going to get a sphere, right? I will get a sphere. But here's the problem. I'm going to get a full, complete sphere. I don't want a full and complete sphere. I want a sphere that has a hole in it. If I just spin that shape around, it's going to be a solid sphere. So that means I got to cut it. right? I got to get this two-dimensional shape, and I got to cut it. So, or actually, let me do this. It would be nice if I could just kind of cut it right like that. And just keep the top part. And if I just keep the top part and I spin that little area that I drew really quickly, I will get a sphere with a hole in it. Do you guys see that? There's going to be a sphere with a hole in it. Because the other way, without me slicing it, I'm just going to get a solid metal sphere. Okay? So now the question is, what's the formula for it? So we'll start off by just kind of drawing this out. They told me that this thing has if I'm going to be spinning it here, okay? Spinning it there. They told me that it has a radius of 3. The hole has a radius of 3, right? So what I'm going to do is I'm going to go by 2s, okay? I'll go by 2s. This will be 2, 4, 6, 8. Same here. You can go by whatever you'd like. I'm just going to go by 2s. So I'm going to have a line right here, y equals 3. Because if I spin that line, I probably should make it nice and solid because this is not the axis of rotation. If I spin that line around in circles, isn't it going to make a hole that's 6 inches in diameter? Right? It's going to go top, bottom, over and over again. And it's going to give me a hole that's 6 inches in diameter. So that's good because that's what I need. Right? And then I need a metal sphere. So I'm going to draw this, but I'm not sure if all the points are going to line up nicely. Okay, I'm just going to draw it for the purposes of having a picture. I'm not saying that's where they intersect, so don't trust my picture right now, okay? Right now we're just drawing something. Here is the area. Okay? There's the area that I'm looking at. Because if I get that area right there and rotate it, I will get a sphere with a hole in it. That hole will have that hole will be of 3-inch radius because that's where I put the line, right? Y equals 3. So it's going to be a 3-inch radius. So when you start rotating, it's going to be a total of 6-inch radius, right? Notice the top of the sphere that I drew is approximately at 5, right? In other words, indicating that the radius of the actual sphere is 5 inches. Okay, so when I rotate it, the sphere will have a diameter of 10 inches total. All right, so there's my picture. That's what I think is going to be good. So now I got to write some equations, right? Because I don't have anything to base my work on. So I know that y equal 3 is one of the equations. The other one is going to be a circle, right? But it's going to be a circle of radius 5 with the center at 0, 0. So it's going to be x squared plus y squared equals 25. Now, of course, we're going to want to solve for y. So y squared equals 25 minus x squared. So y is equal to plus or minus square root of 25 minus x squared. And you'll notice that I have a plus or minus, and I can't use both. So I got to make a choice. Is it the top or the bottom? Right? And you look at your picture, we're going to use the top. So then I'm going to use the positive part of that equation. So 25 minus x squared. So those are my two functions. Now, if I want to figure out where these two functions intersect, again, don't look at my markings because they're probably off, but I just kind of wrote some stuff there. I got to set them equal to each other and solve. Because I already have my two equations. I know my top equation is, let me label it here, y equal to radical 25 minus x squared. I know my bottom equation is y equals 3. So I already have those. I just need to know what are my points of intersection over here. And I'll put right here, not to scale, right? That way you're not going to say like, oh, it's at 6 on one side and at -4 on the other. Maybe it's at -6, maybe it's at 4, -4. Who knows? So let's actually do the work and figure this out. So 3 is equal to the square root of 25 minus x squared. Now I'll take a square to both sides. And I'll move numbers around here. So x would have to be plus or minus 4. So that's good. We know that our intercepts occur at positive and -4. So A would be -4, B would be +4. Okay, now notice my axis of revolution is the x-axis. Okay, my axis of revolution is the x-axis. Now they didn't tell me that that's where I'm going to revolve it. That's where I placed it, because I figure it's going to be really easy to draw a circle if I started at 0, 0, right? So I'm going to make my x-axis the axis of revolution. But you'll notice that the area and those points of intersection are not touching the x-axis, so I'm going to have to connect them. Okay? And now what I'm looking at is all of this area here as my initial starting point. All of that. And then, after I'm done with all of that, then, let me draw this out really quick. So we're going to start off with a shape that looks like this. And then we're going to subtract. What am I going to subtract from that? Because I want to get just this piece here. What do I subtract from it? What do I get rid of? Yeah, the rectangle, this piece right here. I want to get rid of that rectangular shape. So let's draw that out. So a rectangular shape. And that gives me the piece I want. So, what's the top equation for this thing that looks like a piece of bread? This right here. Alright, so y equals radical 25 minus x squared. What's the bottom equation? Y equals what? 0. And from where to where? -4 to 4, okay. The rectangle, what's the top equation? Y equals 3. Bottom equation? Y equals 0. From where to where? -4 to 4. So there you go. I got my two discs. So let's write them out. Volume is equal to pi integral from -4 to 4 of top minus bottom, so radical 25 minus x squared minus 0 squared dx minus pi integral from -4 to 4 of 3 minus 0 squared dx. So there you go. You got disk minus disk. Right, so let's just combine all this stuff. Volume is equal to pi integral from -4 to 4 of square root of 25 minus x squared. Squared will just be 25 minus x squared minus 3 squared is 9 dx. 25 minus 9, that's 16. So it's going to be pi from -4 to 4 of 16 minus x squared dx. And now we integrate, plug in numbers, and we're done. So let's see. We'll be done with this problem here. So that's pi times 16x minus x cubed over 3 from -4 to 4. So we end up with, let's see, 16 times 4, that's 64, minus 64 over 3, minus negative 64, and plus 64 over 3. So when you add all those numbers up, you get 256 pi over 3, because you'll get 128 minus 128 over 3. So you combine those together, you get 256 over 3. So 256 pi over 3. So that would be the volume of the resulting sphere with a hole in it. I'm just curious. I don't think I've ever done this. What would be the volume of the sphere? 4/3 pi 5 cubed, right? Do I have a calculator that's readily available here? Let's see. Just out of curiosity, 4 divided by 3 times 3.141592653, and then times 5 to the third, that's 125. So it's 519.3. So what's 256 divided by 3 times 3.141592653? So 268. So the original problem was 500 and something. Once you cut the hole, it's at 268. So you can see it's lost volume, obviously, right? It was a lot bigger. So I was just curious. Oh yeah, there it is. 519 was the original, if we just estimate, and the one with the hole is 268. Right? 519 and 268. So obviously this got smaller. All right, any questions on this one before we move on to I'm going to put approximately here, 519 cubic units. Any questions on this one? So it's a word problem in a sense that they give you the description. You're going to have to figure out how to draw it, and then what equations can you use. Okay? So this last one that we're going to do is a vertical rotation. Let's see. Example number 6. Find the volume of the solid formed by revolving the region bounded by the graphs and they give us y equals x squared plus 1, y equals 0, x equals 0, x equals 1, and they say about the y-axis. Again, there's that word, right? About. So we're going to graph this thing. I'll kind of graph it right now as you guys are drawing it. So we could probably, let me see, x squared plus 1. We could probably go by half. I think that would be okay. That's 1, 2. And they said I'm going to have to bound it by y equals 0. So that's going to be this line here. That's y equals 0. X equals 0. It's going to be this line here. X equal to 1. And y equals to x squared plus 1. So the area they're talking about is right in here. And they tell me that we're going to be revolving this about the y-axis. Okay? So right here. So, I mean, this doesn't appear like it's going to be a hard problem to do, right? A very basic looking area. And I'm not saying it's going to be difficult, but it's not going to be as easy as just two functions. Whenever you do vertical rotations, remember you go from the bottom up when you integrate, right? So instead of A to B, we call it C to D. So we're going to have to figure out the lowest point that the yellow area goes to and the highest point that it goes to. That can easily be seen right here. Like these intercepts right here represent the lowest points. Highest point would be way up here. Okay, so that's what your C to D is going to be. And I actually did draw it to scale. So you can say that your lowest point is going to be 0 and your highest point is going to be 2. So you're integrating from 0 to 2 in a sense, right? But then you have to integrate right minus left, right? When you do things vertically, instead of going top minus bottom, you got to do right minus left. Look at that yellow area. Is it true that the right function is always to the right of the left side function? So let me zoom in here. So from here to there, to there, to there, is it always true that the right side function of x equal to 1 is always to the right of the left side function x equal to 0? Is that true? Yeah. What about here? Is it still the same two functions I mentioned? No. So it changes. So we need 2 rotations. Okay, we're going to do one for the bottom where, and let me erase this really quick. That way I can kind of break this up for us. We're going to break it up right about here. We're going to do I guess it looks like a square, right? We're going to do a square and rotate that. And then we're going to rotate that thing that kind of looks triangular. And we're going to do it in 2 separate parts and then just add the information, right, that we're getting. So let's see. Let me draw the points of intersection, all of them, okay? So for the square, is it true that the area that's contained in the square is completely touching the axis of revolution at all times? Yes, right? So I don't have to draw any weird stuff. That's just going to be a disk, okay? This is just going to be a disk. So let me write that right here. This is a disk. Is it true that this area up here is always touching the axis of revolution? The top one. The triangular looking one. It has 1 point, but does it always touch it? No. So then we call this a washer. Okay? All of that yellow that I colored in, at some point, the 2 points of intersection have to be on that axis of revolution and they have to be touching, because then that creates a solid shape. But if I rotate that triangular thing around vertically, you're going to notice it's going to create a hole. The top part, the washer, is going to look like this. When you rotate the top part, it's going to have this kind of this type of shape to it. Okay, it's going to have a little hole inside. And once you get a hole, even though it doesn't go all the way through, but once you get a hole in the shape, it's no longer a solid disc. Okay? Sure, it's solid. You might say, yeah, I can pour water in it and it doesn't go through. Correct. But there's a gap between the side to sides. Okay? Even the smallest gap results in washers. Okay? In order for it to be a disc, then it looks more like this. Like, well, forget those two little lines, but it's going to be a nice, solid, hard shape. Okay? So, let's see. Let's do the disc formula first. And then we're going to add it to the washer formula second. Okay? So the disc formula here. Volume is equal to the integral from pi integral from 0 to 1 of the right side function of that disc is 1. And the left side function is 0. And we're going to square it. Okay? If you're not sure what I'm doing here, all I'm doing is I'm piecing together. For the first one, it's just a box, right? The right side function is x equals 1. The left side function is x equals 0. And we're going from 0 to 1. Okay? And then I want to add my washer. And we'll do that right now. So, for the washer, notice how it does not touch the axis of rotation. So I'm going to do this. I'm going to create another square, but then I'm going to cut the square. All right? So I'm going to create another square so that all of this is the area that I'm going to get. And then I'm going to cut out that white part, okay? I'll cut out the white part. That way I get just that yellow part. So here we go. Let's draw this out. So I'm going to get another square. And I'm going to subtract a piece that looks like this. And altogether, it's going to result in a piece that looks like this. Okay, I know it may not look like it just because of the fact that I didn't draw everything like to scale in a sense of one should be lower than the other and stuff like that. If you want me to, I could, but I didn't put them like one on top of the other because they're stacked. I'm just kind of looking at the shapes and saying I need this, I need that, I need that. All right, so what is the equation for this side right here? Remember, we're doing this with respect to y. So your equation must say x equals to. All right, so hold on. I'm just gonna solve for that one. But yeah, you guys said that right. That's gonna be a 1, right? X equal to 1. And what's this one over here? On the left side? 0 from where to where? 1 to 2. Okay. All right, now here. Right side. Now the left side, that one's easy. That's 0. But right side, we have y equal to x squared plus 1. So I'm going to have to solve for x. Y minus 1 equals x squared. So plus or minus radical y minus 1 equals x. Now, a parabola like that, you want to take the positive side so that you get the side on the right. Okay, so radical y minus 1 is equal to x. That's what goes right there. And then for us, it's going to be from 1 to 2 again. So we'll do this in two pieces. We'll do a disk and then we'll do a washer on the side. Okay, so the disk, here's the formula for the disk. The washer, let's write that formula. Volume equals pi integral from 1 to 2 of 1 minus 0 squared. I'm sorry. Oh, no, that's right. 1 minus 0 squared dy minus pi integral from 1 to 2 of square root of y minus 1 minus 0 squared dy. Let's combine that. Pi integral from 1 to 2 of 1 squared, that's just 1, minus square root of y minus 1 squared is going to be just y minus 1, so it'd be y plus 1 once I put it together, dy. So volume is equal to pi integral 1 to 2 of 2 minus y dy. Before I move on, are there any questions on any of the two formulas? The disk formula, which was written up here, the v equal to pi 0 to 1 of 1 minus 0 squared dy for the disk, and then for the washer, right here. The hardest part about these problems, besides the fact that we had to break it up into multiple parts, but is the fact that you got to remember that you're dealing with dy, so you got to remember to solve for x. They don't always give you the equations in the right form, so you may have to rewrite them, okay? All right, so let's combine these two things because we got to add them, right? So let's combine the disk and the washer. So the disk, I'm going to put V sub D just for my reference, okay? The disk is pi from 0 to 1 of 1 dy, so pi 0 to 1 of 1 dy. So let's find the answer for that one. That's pi of y from 0 to 1. So that's pi of 1 minus 0. All right, so that's nice. That's an easy answer. So the volume of the disk is just pi. Now let's do the volume of the washer. So pi integral from 1 to 2 of 2 minus y dy. So that's pi 2y minus y squared over 2 from 1 to 2. It's going to kind of work vertically from here. So this is 4 minus 4 over 2 minus 2 minus 1 over 2. All right, so 4 minus 2 is 0, so this is just a pi over 2. So here's one of my answers, and here's the other answer. So to find the full volume, I'm going to get the volume of the disk plus the volume of the washer, which is equal to pi plus pi over 2, which is 3 pi over 2. Let me kind of zoom out here. I mean, I can't zoom out enough to show the whole problem. So you can see how this is kind of extreme here. But let me just pause this for a second. It's not paused. All right, so I'm going to give you guys the homework, including the stuff I already gave you. So you can just add on to it. Okay, so page 465. If you already did the 1 through 4 and 7 through 10, that's fine. If you haven't, then your assignment is 1 through 16, 19 and 20, 31 through 34. So that's all of it. Okay, so if you already did those other ones, then great, you have less to do. If you have questions, always just ask and we can go over it. Like I said, I did have scheduled a test over section 7, 1 through 7, 2, but I don't know if I'm going to test you guys over it. I really don't think so, because once we start studying for the AP exam, there will be questions like that on the AP exam. I can almost guarantee you that there will be an area problem and a volume problem on your AP exam. Okay, as you guys start seeing when we start studying in class, you're going to notice there's pretty much one in every single FRQ, at least one. So, so yeah, so practice on this homework.